Good morning everyone. So in the last two classes we were focusing on vertex coloring. In today's class we are going to talk about edge coloring. So for the edge coloring the same rule works that two adjacent vertices should have the different color or two non-adjacent vertices can receive the same color, and we need to find the minimum number of the colors required to color the edges of the graph. That would be called as the edge chromatic number, which is denoted as chi dash g. Okay, let's see some examples. So let's assume that we need to find the edge chromatic number for K4 and K5. Both are drawn here. You can try this exercise by yourself. If we look for K4, then we can begin with U1, this vertex, and you can see that there are three edges which are incidenting here. It means that all three edges are adjacent and therefore they all must have the different color. So 1, 2, 3 is given, and then there are three more edges. We can look at them one by one. So if you see this edge U2 to U4, it is adjacent to the edges with color 1 and 3 but not with the color 2. So color 2 is given. If you see U2 to U5, then it is adjacent with 1 and 2 but not 3, and similarly 1 can be given here. So the edge chromatic number of K4 is 3. Similarly, you can quickly try the edge chromatic number for K5 and it comes out to be 5. So the edge coloring for K5 is shown here, and which means that in case of vertex coloring, chromatic number for Kn was n, but in case of edge chromatic number, it's n if n is odd and it's n minus 1 if n is even. So well known Petersen graph, if you try to compute its edge chromatic number, it comes out to be 4. We haven't proved it why it's 4. We will discuss it later, but you can try to color it with 4 colors and you can observe by yourself that it cannot be colored with 3 colors. Find the edge chromatic number of path graph, cycle graph and complete bipartite graph. So path graph is very simple. If I draw any path, I can give the color 1, 2, 1, 2 and so on. So 2 colors are sufficient. In case of the cycle, if it is an even cycle, then 1, 2, 1, 2 would work. But in case of the odd cycle, 1, 2, 1, 2 and the third color is required. In case of the complete bipartite graph, if you let's say CK2, 3, then you can give 1, 2, 3 color here. Then if you see this edge, it is incidenting with color 1, so I can give color 2 here. If you see this one, it is incidenting with color 2 on both the sides, so I can give color 3 here and I can give color 1 here. It means that it is maximum of m comma n if the complete bipartite graph is Kmn. So this is the table which says that path graph 2, cycle graph n even 2, n odd 3, Petersen graph 4, KRS complete bipartite graph, maximum of r comma s, and then Kn. Find the edge chromatic number of the following bipartite graph. So if you try it, so you can start with any vertex with maximum degree 1, 2, 3 and then try to see each adjacent edges one by one, and you will see that it comes out to be 3. And the more important observation is that for the bipartite graph, the edge chromatic number is equal to delta G. So we will quickly see the proof of this theorem. We will do it by induction on the number of the edges. It means that if we remove one edge, then the obtained graph G dash is G minus E. Now we are not giving any preference to any of the edge, so you randomly remove one edge with endpoints U, V, and then we assume that by induction that for G minus E, it can be colored, the edges can be colored with delta colors, and when we put back E, then one of the color can be used for E. Okay, now each of the vertices U and V, so this is edge E, this is U, this is V. Now we know that the degree of the graph is delta, and when you delete this edge E, so in G minus E, the degree of U should be less than delta and degree of V should be less than delta. So if there is a color that has not been used on any of the edges with U as in, it means that, so U, this is U and its neighbors are less than delta, its maximum degree can be delta minus 1 in G dash, and we know that we have delta colors available. It means there is at least one color which is not used by the neighbors of U. Similarly, there is not a color, but there is at least one color which is not used by the neighbors of V. We call it I and J. Yes, so this is the situation. There is U, there is V, there is a color I which is not used by these neighbors, and there is color J which is not used. If this color I and J are same, then there is one color which is not used by these neighbors as well as these neighbors, so I can use that color for E and I am done. Yes, let's say 2 is here and it's like 1, 3, 4, 6. There is a problem now. There is a color which is, if I is not equal to J. If I is equal to J, well and good. But if I is not equal to J, then you cannot use, you don't have an available color. So if I is equal to J, then we can color E by that color and we are done. The problem comes when I is not equal to J. So assume that the color I is available at U but absent from V, and color J is available at V, absent from U. It would be clear from a figure. So let us consider this bipartite graph. I delete the edge AG, which I call as edge E. After deleting it, A has the colors 1, 2, 4. Let's assume the color 1, 2, 3, and G has the color 1, 4, 3. It means that 4 is absent here and 2 is absent here. So I is not equal to J. Yes, it means that to AG, if I give color 4, then it is creating a problem because it is incidenting to an edge with color 4. If I give it color 2, then it is incidenting with an edge with color 2. So both the possibilities would not work. So now let K be a camp chain. Camp chain is simply an alternating path, or it's a path where edges are colored alternatively, different colors. So let's say A, B, A, B, A, B, something like this. Yes. Now you have U, you have V, and there is a camp chain. We claim that there cannot be a camp chain of different colors from U to V. So for example, I, J, I, J, I, J, and I. Yes. Why it is not possible? Because it's a bipartite graph. So when it's a bipartite graph, then the path length is odd. So let's say the path length is 5, 7 or 9. In this case, the path length is 1, 2, 3, 4, 5, 6, 7. So it's odd. So if you are starting at I then you must end with I. But it is not possible because we have claimed that I is present here, but I must be absent here. So since the path length must be odd, there cannot be this camp chain or an alternatively colored path from U to V. Yes. So a camp chain is this, and we claim that V does not belongs to the camp chain. So this is the situation, and this is what we are claiming, that if you start with color 2, then 4, then 2, then 4, and then again 2 is not possible here, because we have already assumed that 2 is not here. You can see that 2 is absent from here. Otherwise, if 2 are present at both the positions, then of course we can use the color 4 for edge AG. So there cannot be a camp chain here. It means that what I can do is that if I replace these color 2, 4, 2, 4, then there is no harm. Yes. So what I can do is something like this. So 4, 2, 4, 2. 4 was already here. So I am changing these colors alternatively. So if there is a camp chain like this, A, B, A, B, not a camp chain, but if they are alternatively colored, and there is no, so it's not present here, then instead of A, B, A, B, there is no harm in writing B, A, B, A. This is what we have done. It would not have been possible if there is a camp chain from A to B. If there is a camp chain and 1, 2, 1, 2, 1, 2, then you cannot interchange the color. So it is only possible, or we manage to interchange the colors because there is no camp chain, and there is no camp chain because the same color cannot be available at both the ends. And when we interchange this one, then what exactly happened here is that I have color 4 here and color 4 here. So color 2 is not used at any of the endpoints, and I will use the color 2 for edge AG. So little bit longer theorem, but if you read the proof by yourself and follow the instruction which we have discussed, then you can easily understand it. Okay, so quickly now we can try to find the edge chromatic number of K 4,4. So we know that for the bipartite graph it's delta G, so edge chromatic number is 4, so it can be easily colored with 4 colors. So for the complete bipartite graph, it is maximum of m comma n, which is equal to delta G. This is a very important result. It's difficult to prove, but we can use it to find the chromatic number, which says that let G be a simple graph, then the edge chromatic number can either be delta G or it can either be delta G plus 1. There are only two possibilities. Yes, so in case of the Petersen graph, it comes out to be delta G plus 1 because the maximum degree is 3, or in some cases it comes out to be delta G. And this is a quick observation which shows that chi dash G cannot exceed 2 delta G minus 1. This is very simple because for any edge E, it can have, U can have delta neighbors and V can have the delta neighbors. The worst case is you can give the different colors to all the neighbors. So neighbors means here the edges, and therefore 2 delta colors can be required. But when you are counting 2 delta color, then this is also the neighbor of U and as well as V. So it has been counted twice in this 2 delta, and since there is only one common neighbor, so it should be 2 delta minus 1. So this is can be used to develop a greedy algorithm which says that there is always possible to have a proper coloring or proper edge coloring with 2 delta minus 1 colors. So that's it from today's class. This chapter is over. We will discuss the tutorial sheet in the next class. Thank you.